Hello everyone, welcome to Tuteetute. In the previous lecture, we have seen about the perpendicular polarization. Now we will continue the discussion regarding this parallel polarization. As we have studied the perpendicular polarization in very detail, so here same thing will be there. Okay, the definitions, whatever plane of incidence and interface, normal to the interface, Snell's law, all these things are same. Okay, so quickly we can able to finish this one. We'll see one by one. Okay, so first we'll study this structure. Okay, how the incident wave, reflected wave and transmitted waves will be oriented according to this particular parallel polarization we have to see. So as this particular name given, the information parallel polarization. So as I said, in our perpendicular polarization also, this name was given according to this plane of incidence. And this vertical polarization and H polarization are given according to interface concept. Here also same thing. Okay, so first we will define this parallel polarization, the incident electric field or the electric field concept. Okay, whether it is incident electric field or reflected electric field or the transmitted electric field, the electric field, one of the component or electric field is in the plane of incidence or parallel to plane of incidence. That is why it is called parallel polarization. Okay, accordingly we will give the structure here. So as per our previous discussion only, the boundary I am taking as xy plane. So boundary is xy plane. This is the x-axis, y-axis is coming towards you. So that this is the boundary which is separating the medium 1 and medium 2. Okay, so this is medium 1, medium 2 having the characteristics mu1, epsilon 1, sigma 1, and medium 2 having the characteristics mu2, epsilon 2, sigma 2. So that it is having the impedance eta 1 and medium 2 is having the impedance is eta 2. And the wave incident like this is an incident electromagnetic wave. It has been incident like this by making the angle theta I with normal to the interface. So normal to the interface is z-axis. So theta I is the angle of incidence. And this is a reflected wave which is making the angle theta r, and according to Snell's law of reflection, theta r is equal to theta I. And because of the impedance mismatch only, this reflection has possible, and remaining part will be transmitted into the medium 2. Same thing. Okay, so here theta t like this we have to take, but we are studying here about the parallel polarization. So electric field should be available in the plane of incidence. That means magnetic field is perpendicular to the plane of incidence. What is the plane of incidence in this case? The plane which contains normal to the interface and the incident electromagnetic wave. These two are available in which plane? XZ plane. So here interface is xy plane, normal to the interface is z-axis, same thing. Okay, plane of incidence is xz plane. Snell's law already we have studied. Okay, so here electric field is available in the plane of incidence or parallel to the plane of incidence. So magnetic field is perpendicular to the plane of incidence. So this is HI now. Magnetic field is perpendicular to the plane of incidence. So here also this HR we have to take like this. This HT we have to take like this. Okay. Then how to represent the electric field orientation? Again by using the right hand thumb rule. This is the direction of propagation. This is the electric field orientation. This is the magnetic field orientation. This middle finger is representing the magnetic field orientation. So this forefinger is representing the direction of or orientation of the electric field. This thumb is representing the direction of propagation. So suitably we can able to take like this. So electric field is coming like this. Now you see electric field is oriented like this in the plane of incidence. That's why it is called parallel polarization. Okay. One thing you observe, I have taken here this H field is coming outside, but I did not represent here. Why means it is going inside. What is the reason for that? Like this we did not take in case of the perpendicular polarization. Why did we take like this means, if you make theta is equal to 0, if you make theta is equal to 0, whatever the results we are getting from this one, these things must be comparable to the normal incidence case. Okay, so we can compare like this. So for example, in case of the normal incidence, listen carefully, same interface, same normal I am taking. Normal incidence means, for example, this is the electric field orientation, EI, this is HI, this is the direction of propagation. It is about incident wave. Okay, now because of the impedance mismatch, what is happening? Wave will be reflected back now, something. So when the wave is reflected back, this is the, now we are representing like this. This forefinger is representing the electric field, thumb is representing the direction of propagation, this middle finger is representing the direction of the magnetic field. Forefinger is representing the electric field. So it is going, striking the interface, XY plane. Because of the impedance mismatch, it will be changing like this. Its direction is changing like this. That means one thing you observe, we did not change the electric field orientation. Whether it is incidenting wave, electric field is oriented like this only. Whether it is reflected wave, electric field is represented like this only. So we did not change the electric field orientation in case of the electric field and in case of the incident wave and reflected wave. In order to follow this one, direction of propagation must be reversed. Na? It should be in the negative z direction only, because it is the reflected wave. Incident wave is in the positive z direction, so reflected wave must be in the negative z direction. To satisfy these two, the magnetic field is reversed. Okay, once again you can check here. This is the incident electric field. In this case, the magnetic field is coming out of the screen. When we are looking for the reflected wave, the magnetic field orientation is going into the board. So that I have to take here circle cross. So this is indicating the reflected magnetic field is going into the board, going into the plane of incidence. Okay. Next, what about this transmitted wave? It is similar to incident wave only. Transmitted electric field is like this, oriented in the positive x direction only. This is the direction of the propagation of the transmitted wave along the positive z direction, and this is the orientation of transmitted magnetic field coming out of the screen, that is actually in the plus y direction. So this HR direction is going into the board, that means in the negative y direction. So to get this particular structure, by making theta is equal to 0, how will get this thing? How can we make this one? Just by taking the angle of incidence is equal to 0. If you make this theta is 0, what will happen? Instead of incidenting like this, we have to incident like this. Here theta I is not equal to 0. Here theta I should be equal to 0. Just we are making theta is equal to 0. Just by making theta is equal to 0, this wave will be like this. That means in this way we will get. This is the incident wave. Na? So HI is coming outside only. Electric field, instead of this one, it will come like this, oriented in the plus y direction, and it is going like this. And as I said earlier, this magnetic field should be going inside. Huh? That is why here we are taking inside. That's why here cross circle will come. Okay. So in this way we are representing all these things here. Now we'll proceed to the next part of this particular lecture. That is Snell's law, already we know. Here also same thing. Now why it is called P polarization? So nothing is there. Parallel polarization, P polarization. According to German's word only. Again, how we have taken S polarization. Okay, Senkrecht is there na? S polarization according to the German word, that is for the perpendicular polarization. And here also this thing we are taking P polarization. Okay, perpendicular polarization means S polarization, parallel polarization means P polarization. And this parallel polarization name was given according to plane of incidence. This vertical polarization and H polarization are given with respect to interface. Okay, now you see how we have given this one. So with respect to interface, this one of the component of the electric field is perpendicular to the interface. That is why it is called vertical polarization. Okay, and we have taken the previous case, that is perpendicular polarization, as E polarization, because E is parallel to interface. Okay, that is called E polarization. So it is opposite to that one, we can take it is a H polarization. That is the thing. Okay. Now we will take expressions for the fields in case of this parallel polarization. Okay, this expressions related to parallel polarization. So for that, once again I will draw the structure related to this one: incident wave, reflected wave, transmitted wave. So as per our discussion, HI must be coming out of the plane of incidence, HR must be going into the plane of incidence, HT must be coming out of the plane of incidence. So electric field orientations how to give? This is the way. H is like this, so E must be towards this side. Then we can close like this. It will represent the direction of propagation. So this is EI. And in this case, see carefully, H is going inside. Okay, so that if I keep like this, thumb is representing the direction of propagation. If E is like this, then we can close like this. Okay, this is the direction of H field, so E must be like this. E closing towards H, thumb is in the direction of propagation. So this is ER. And by seeing this one, we can write ET like this. Okay, this is what we need to understand. Now, according to the boundary conditions, tangential components of the electric fields and magnetic fields are equal, because we did not consider any current components or the charge on the boundary. So that here anyhow HI is tangential to the boundary, HR is also tangential, and HT is also tangential. So that accordingly we can write HI plus HR is equal to HT. Like this we can take. Now for the electric fields also we have to write the expressions, and as I said earlier, we need to get the tangential component, but this electric field is oriented in the arbitrary direction. So what we need to take? This component we have to take. This is a tangential component of the electric field for the incident wave with respect to the interface. And here also we have to take the tangential component towards this side. How to get that one? This is actually the tangential component of EI. So we have to resolve this EI into tangential and normal, and we need only tangential. And same approach we have to apply for this ER and ET also. So what we can able to write here, because it is making the angle theta I, we can write here EI cos theta I, and in this case it is ER cos theta I. Why I am taking the both angles are theta I? Because of this Snell's law, we can able to tell theta I is equal to theta R. So that we can take here ER cos theta I, this is equal to ET cos theta T. So now we have applied the boundary conditions related to magnetic fields and electric fields. So that now according to this particular expression, we need to convert into electric fields only. So HI-EI relation is given by eta 1, HR and ER relation is given by eta 1, HT and ET equation is also related by eta 2, that is related to eta 2, because these two are available in the medium 2, so that we have to take eta 2. And incident wave and reflected wave are available in the medium 1, so those are given with respect to eta 1. So this particular expression can be changed like this now. So EI by eta 1, and it is ER by eta 1 only, because as I said earlier, related to medium 1 only. But here, because it is a reflected wave and it is an incident wave, if you see the orientations here, these are opposite to each other. So that here we can keep here minus symbol. It is equal to HT is given by ET by eta 2. Like this we can able to give. Now we have two equations related to electric fields only, so that we can able to get the ratio of this reflected wave and incident wave to get the reflection coefficient, and we can get the relation for ET and EI to get the transmission coefficient. So this is equation 1 and this is equation 2. Now I am looking for this reflection coefficient in case of the parallel polarization. Reflection coefficient means generally gamma, and we are working for the parallel polarization, so that this symbol was given. So it is equal to what we need to do, reflected electric field by incident electric field we need. So in this particular expression, now we need to remove this ET by using equation 2, so that you will get the terms related to ER and EI, then we can able to get the ratio. So further we can able to write this equation 1 we are modifying actually, that is EI cos theta I plus ER cos theta I, it is equal to, ET should be replaced according to equation 2. So ET is here, so what we can write, EI by eta 1, this is multiplied with eta 2, minus ER by eta 1 multiplied with eta 2. This is ET, but this everything is multiplied by cos theta t. Okay, now if you see the expression, we have EI terms and ER terms. So write EI terms at one place and ER terms at other place. So what we will get here, so EI times of, it is cos theta I, and here also we have EI term and it is positive term. So if you send this side minus, here what we have, eta 2 by eta 1 multiplied with cos theta t. This is about EI terms, and it is equal to, here we have ER terms, here minus is there, minus ER eta 2 by eta 1, and it is cos theta t. This is one ER term, and here also we have the ER term. So that one I am writing here, by sending this side we will get minus ER cos theta I. Like this we can write. Okay. So EI times of cos theta I minus eta 2 by eta 1 cos theta t, that is equal to, we got minus ER eta 2 by eta 1 cos theta t minus ER cos theta I. So we need to get the ratio between ER and EI. So I am writing like this, EI times of, here we can take a LCM, that is eta 1 we will get, so eta 1 cos theta I minus eta 2 cos theta t. Okay, by eta 1 is there, here also LCM will be eta 1, both will be cancelled. So it is equal to, here two terms are having the minus, so that minus we can send this side, so this first term will become minus and this will be plus. So here, now by taking ER common, what did we get, eta 2 cos theta t, and here because minus is already taken, here plus eta 1 cos theta I. Okay, this is what we can get. Now we need to get, as per our reflection coefficient definition, ER by EI we need. Okay, so we sent this one to this side, so this will be the numerator, that is eta 2 cos theta t minus eta 1 cos theta I, by this term we have to write, that is eta 2 cos theta t plus eta 1 cos theta I. So this is what we can get. What is this one? Because it is the ratio between reflected electric field and incident electric field, this is the reflection coefficient. This one we have done in parallel polarization, so gamma parallel. So this is the relation we got. Okay, now this transmission coefficient also we have to get. For that, once again I am writing the relations by drawing this particular structure: incident wave, transmitted wave, reflected wave. Okay, so what are the equations we got previously? Reflection coefficient already we have done in the previous slide only. So here I am writing the transmission coefficient related things. So HI plus HR is equal to HT. Next EI cos theta I plus ER cos theta I is equal to ET cos theta T. Okay, just according to the boundary conditions we have written these two equations. Then the first equation can be modified into electric fields. So EI by eta 1 minus ER by eta 1 is equal to Et by eta 2. This is what we can do. Okay. Now we need to get the transmission coefficient that is tau parallel is equal to, it is a ratio of Et and EA. This is what we need. So we need to eliminate here ER terms. Okay. So use this equation, and for the time being I am taking it is equation 1, it is equation 2 for this particular slide. So using this equation 1, we need to replace ER. Then you will be leaving with the ET and EA. So you can get the relation. Okay. That is EI cos theta I. This one I am writing now. And ER should be replaced using this particular equation. So first I am writing cos theta I. Then ER is there. So how to write ER? You need to send this term this side. And remaining terms are EA by eta 1 minus ET by eta 2 multiplied with eta 1. Okay. So from this equation we have written this one instead of ER cos theta I is available here. So it is equal to, right side of this is equation 2 is ET cos theta T. Like this we can write. Okay. Now write all the EA terms at one place and ET terms at one place. So EI cos theta I and EA we can take common also. So this term is over. Now you see this one. Here eta 1 will be cancelled. So EA cos theta I will be there. That is already there here. So simply cos theta I. That means it is coming 2 times actual. Now it is equal to, here ET term is there. We can send this side. Here also ET term is there. So ET I am taking common. So what is there here? Cos theta T. And from here minus is there. So by sending to right side it will become plus, and eta 1 by eta 2, and this is cos theta I. This is what we can get. By taking LCM we will get eta 2 that can be multiplied here. So we will get 2 eta 2 cos theta I EI is equal to, what did we get here? ET times of eta 2 cos theta T plus eta 1 cos theta I. This is what we can write. Now get the ratio of ET and EI. This one we can write tau parallel is equal to, what did we get here? Numerator will be 2 times of eta 2 cos theta I by denominator will be this one, that is eta 2 cos theta T plus eta 1 cos theta I. This is what we can have. So transmission coefficient for the parallel polarization is also over. Now these relations I will write here. Whatever we got, that is gamma parallel is equal to, what did we get? Eta 2 cos theta T minus eta 1 cos theta I by eta 2 cos theta T plus eta 1 cos theta I. Next tau parallel is equal to 2 eta 2 cos theta I by denominator is same thing, eta 2 cos theta T plus eta 1 cos theta I. This is what we got. Okay. So for comparison purpose, here I will write gamma perpendicular also. Okay, gamma parallel, gamma perpendicular I am going to write. That is eta 2 cos theta I minus eta 1 cos theta T by eta 2 cos theta I plus eta 1 cos theta T. Now tau perpendicular is equal to 2 eta 2 cos theta I is by eta 2 cos theta I plus eta 1 cos theta T. These are the equations we got for reflection coefficient and transmission coefficient in case of perpendicular polarization, and these are in case of parallel polarization. Reflection coefficients, transmission coefficients. Okay, just you see the change what is there in case of the reflection coefficient. Eta 2 minus eta 1 by eta 2 plus eta 1. So as I said, if you make theta is equal to 0, it will give the equation for the normal incidence. Here also same thing. If you make theta is equal to 0, it will give the equation for the normal incidence. But what is the difference you are observing here? Just cos theta t and cos theta I are interchanged. So that from this equation you can remember this equation. Okay. And next thing is, here numerator part is same in case of the transmission coefficient. Numerator part is same in both. You can able to observe that one. 2 eta to cos theta I. Next thing is, in case of perpendicular polarization, already we have proved that 1 plus gamma perpendicular is equal to tau perpendicular. This is what already we have proved. Now we will check whether it is true or not. In the time of this perpendicular polarization only, I have said that this is not followed in case of the parallel polarization. You can check that one now. So for that particular purpose I am taking 1 plus gamma parallel. What will happen? Plus 1 will be there. This will be added to the numerator. So what we will get? 2 times of eta 2 cos theta t we will get by eta 2 cos theta t plus eta 1 cos theta I. This is what we can get. It is not equal to tau parallel. Okay. So 1 plus gamma parallel is not equal to tau parallel. That is what we can tell, because here cos theta I is there, here cos theta t is there. So this is surely not equal to tau parallel. But what is the equation we can give? So what we need to do? This one is to be removed, and in place of this one we need cos theta I. That means 1 plus gamma parallel must be multiplied with cos theta I by cos theta t. This part is this one. So if you multiply it with cos theta I, this numerator will be fulfilled, but this cos theta t should be cancelled. That's why in the denominator I have taken. So it is equal to, now it is exactly equal to tau parallel. So this is the relation we can give. Okay. And here gamma and tau relation in case of the perpendicular polarization is similar to normal incidence only. But gamma and tau relation in case of the parallel polarization is different from that one. And that exact equation is this one. Okay. This is the relation we can able to tell. Thank you.